So number 6 here is the same calculation as number 5. We're not going to spend a lot of time on it. The only difference being is that before it was evacuated of nitrogen and oxygen. Now, see, let's go back here. There was no nitrogen, no oxygen. They put this in. Number 6 is the reverse scenario. There's no nitrogen monoxide. There are products. Because there are products, this reaction will move backward. We will be subtracting from the products, adding to the reactants, plug it into the expression, solve for x. Ooh, 007. That amuses me. We plug these things back in, everywhere x is, and we get these values. And let's see if the check for k worked any better this time. I'm reticent to do this because it might not work. Let's see. I only got 33. That's still not pretty. Yeah, so that didn't come out as perfect as I hoped it would. Oh, wait a minute. I forgot to square. Yeah! I'll take that. So I had forgot to square this when I did my K check, but when I went back and did the K check, I got 2,378. This is only 2 sig figs, so I should take the first 2, round up. Oh yeah, 2,400 is K. So we were able to get this K this time because I had enough sig figs to really get in the ballpark. That last one, I wasn't too happy when I only got into thousands, but that's the problem with sig figs. Sometimes when you subtract, you lose values, and then you're kind of stuck. Number 7 is a very different type of problem. In fact, let's take 2 seconds and talk about what should you focus on, what should you get worried about. You're not going to have a ton of these solve this versus K. These solving for X things are maybe one part of one free response question. You're not going to have that. The Rice table, though, that organization of data is huge. When you organize the data, it then provides you a format to answer other questions. What might happen, though, is after you've got all this data organized, they may then tell you, hey, by the way, this thing is equal to, I'm just going to make a number up, 45. And if 45 is equal to 2x, well then x is equal to 22.5. And if x is equal to 22.5, you can fill in the rest of the data table x values, and boom, you've got it. That's much more common than using the solver function, or using the quadratic equation, or using guess and check to solve for that minuscule little x. That's not as common. So let's look at number 7, which is a much more common scenario. Okay, I just lied. I thought this was a different question. Number 7 is the same scenario. We'll come back to this one in a little bit. Let me find. Searching here. All right, well, we'll come back to this idea in a minute. Where was I? So number 7 is pretty much the same idea. Again, we have 4 moles of this and that, so in 1 liter, so 4 moles per 1 liter is 4 molar, 4 moles per 1 liter is 4 molar. It is entered into an empty flask, so there's none of this. Then I can do my setup. They give us the equilibrium constant. The equilibrium constant for the following reaction is, oh, there's K. I can set it up, I can solve for x, I can plug it back in. It's the same thing again, like the last problem. Organizing your data makes it much easier. Same thing with number 8. The following reaction has an equilibrium constant of 620. That's K. Calculate the equilibrium concentration if all the species, if 4.5 moles of each component were added to a flask. So they started off with 4.5 moles of each thing into a 3-liter flask. So you have 1.5 molar of all 3 solutions. So it's 4.5 divided by 3, 4.5 divided by 3, 4.5 divided by 3. So you have 1.5 molar for each of these solutions. It says K is equal to 620. Now to me, I see 620, and I know automatically this reaction is going to be shifting to the products, because that means there's 620 products for every one reactant, so it's going to heavily favor the product side. You might want to take a Q though. So Q would be 1.5 squared divided by 1.5 times 1.5. Oh, I can do that in my head. That would equal 1. So Q is equal to 1. 1 is far less than 620. We need a whole lot more products to get it to 620, and a whole lot less of these reactants to get it down. Get the reactants down, the products up to get it to 620. So remove reactants, add products to get it to 620. So we have 1.5 plus 2x squared, 1.5 minus x times 1.5 minus x. Like both of these would be on the bottom, so I just hit up a square to simplify my work. Solve for x. X was 1.3. Plugged it back in. And again, you could check these three values to see if they came out close to 620. Number 9. Strike it, reverse it. No, it's actually the same thing again. There is one different thing about number 9. So let's look. We have ammonia. It's aqueous. Water is a liquid. Liquid. Don't care about liquids. They don't impact the equilibrium position as long as they're present. So I just scratched it out because in here it would be represented by a 1. Got the ammonium, right? This is ammonium. That's ammonia. I feel like I'm in Latin class right now. We have hydroxide, but there is no hydroxide. Just solution is originally 0.2 ammonia. And we're supposed to calculate the other pieces as it moves along. So we have to assume we're removing ammonia as we make these products. So we have x times x, or x squared, 0.2 minus x. Here we go. That's our expression we need to solve somehow. We get x, we plug it back in, and we have the values at equilibrium. Should be checkable. 0.2 times 0.2 divided by 1.98. We only have one sig fig, so don't expect a miracle there. 0.002 times 0.002 divided by 0.198. I got 2 for my k check. I'm going to write this k check. I got 2 times 10 to the minus 5th, which, because I only have one sig fig, darn close to 1.8, and that makes me happy. Number 10, same idea. Equilibrium constant for the following reaction is 600 degrees. What is this? We don't really need this. The 600 degrees Celsius is just an acknowledgement that at this temperature, here's K, because this is K, the equilibrium constant, and here's a useless clause, is 4. If you change that temperature, which we're not going to do, then the K would be different. Initially, 2 moles and 1 mole were mixed in 1 liter. Except this time, water's a gas. 2 moles per liter, 1 mole per liter, 0, 0. Set it up, subtracting from the reactants because there are no products, so we have to add to that side. Plug it all into the equation, solve. All right, this is one of the special scenarios. I'm going to stop for now, and then I'm going to pick up at 11, where you have a different, more unique scenario that I like.